Hi everyone, I'm Sarah Tymochko. I am a grad student in the Department of Computational Math Science and Engineering at Michigan State University. Today I'm going to be talking about using zigzag persistence for bifurcation analysis. This is joint work with my advisor, Dr. Liz Munch, and our collaborator, Dr. Frost Casone. So to get started, I'm going to sort of assume everybody has a background in persistent homology. However, just to recall the basics, persistent homology is a tool from topological data analysis to extract shape from data. So particularly for this talk, we're going to focus on point cloud data, so a collection of points with a notion of distance. On the left here, you can see an example of a point cloud that sort of has these two circular shapes. And additionally, we've connected any points that has distance less than 0.7. So we're going to use the Vietoris-Rips filtration here. So additionally, anywhere you see three edges between three vertices, that triangle would be filled in, and so on for higher dimensions. However, those pieces aren't shown in the figure for simplicity. So what we're going to do is look at this complex as we change the distance value. So we're going to connect any points that have distance less than what's shown here, and we're going to track when features like circles and connected components appear and disappear. So on the right here, the orange points correspond to circular structures. So we can see that this point here corresponds to the smaller circle, while the higher up, further off diagonal point corresponds to the larger circular structure. So this encodes the topological structure of the point cloud in this persistence diagram. Just to go into a little bit more detail, to start out, we want to be given a collection of simplicial complexes with inclusions. So using the Vietoris-Rips filtration, we have these natural inclusions because as you're increasing that distance value, you're adding more and more simplices. And so these inclusion maps induce maps on the homology groups, which give you a sequence of vector spaces and linear maps called a persistence module. For this particular example, we're going to use a generalization of persistent homology called zigzag persistent homology. So we're still going to start with a collection of simplicial complexes, but now rather than having those inclusions all going in the same direction, we can have inclusions that go in different directions. So in this case, that's shown here, we can see that we have an inclusion first going to the right, then to the left, then to the right, and alternating. In general, we could have any sequence of inclusions in any direction. However, for this particular case, we're going to focus on that alternating, and I'll explain a little bit more about that later. But regardless, these inclusions induce maps on the homology groups, where the maps on the homology groups go in the same direction corresponding to the inclusion. So again, we have that sort of zigzagging pattern here on the homology groups. And this is called a zigzag module. So zigzag persistence still gets you a persistence diagram. However, in this case, the birth and death pairs don't necessarily correspond to scale like they do in the Vietoris-Rips filtration. Here, what they're going to correspond to is the location in the zigzag. So looking at this basic example, we're going to start with three simplicial complexes across the top here. And in the middle, we're going to take their unions. So we're assuming we have some sort of information about where these simplicial complexes lie geometrically in relationship to each other. And also for the sake of this example, these triangles are not filled in. So we can see that we have a circular feature here in red that starts at the beginning and it is included into the union. However, it does not continue going forward. Whereas we have this blue one that starts in the union and continues through to the next union, but disappears in the last simplicial complex. So looking at the zigzag persistence diagram, we're going to have a point 0, 1, and that's going to correspond to this red feature that appears at the beginning in the 0th simplicial complex, but it dies going into the first one. Whereas the blue point, or the blue circle, is going to have coordinates 0.5 and 2. And so it's going to be born at 0.5 because it's in this union. So we're going to consider these sort of half indices. So it starts here in 0.5, it still exists in 1 and 1.5, but it dies going into 2. So now, rather than having birth-death pairs corresponding to some scale of how large that circle is, instead it's going to correspond to how long through this zigzag does that same feature persist. So the starting motivation here is, can we detect the range of the point clouds that are the most circular? So here we have an example of 5 point clouds, all just drawn from circles of different radii. And we can see that the circles on either end are pretty small compared to the circles in the middle. So we'd want to detect the fact that this range of circles is the most circular in some sense. So we're going to start out with our collection of point clouds. And again, we're going to take the unions in between. So this will allow us to see how the structure is changing as you transition from one to the next. So looking back at our example, that gives us these corresponding point clouds. However, we know that the homology of point clouds is uninteresting as they're all just separate points. So what we're going to do is apply the Rips complex for a fixed radius. So rather than having that changing radius like on my first slide, we're going to fix one value, connect everything with pairwise distance less than that value, and that's going to give us a Rips complex. So in general, we could use the same radius across each Rips complex, or more generally, we could use a different one for each original point cloud, and then in the unions, we would take the maximum of the one on either side to ensure that those inclusions still hold. So doing that for our particular example, here we're going to use different radii, but we can see that sort of zigzagging pattern where we see there's a little circular feature here at the beginning, but it gets filled in the union. But going to the next one, we see the same sort of circular feature persisting through the middle as that circle sort of shrinks. And then finally at the end, we get that that circular feature is going to die off again. So now we have our zigzag of Rips complexes, we compute the homology at each step, and we're going to track homological features through this zigzag. And this can be computed using the Dionysus 2 C++ and Python package. The link is on the slide for that. So our starting example is going to be these simple circles. So we have the 5 circles, as I mentioned, where the circles on either end are pretty small. And we really want to detect this middle region as our circular feature. We're going to compute the zigzag persistence. And when we get our persistence diagram, we have a point, the furthest off diagonal one-dimensional point has the coordinates 1 and 3.5. So that indicates that there's a circular feature that is born at time 1 and persists through the zigzag until it gets to 3, and then it's going to die at the union between 3 and 4. So that's picking up that range of values that we wanted to see. It's detecting that that's the most circular range in this sequence of point clouds. Okay, so now we've shown that this works on a basic proof of concept example where we started with some circular data and we were able to pick up the most circular region. But as my title indicated, this talk is going to connect back to bifurcation analysis. So now let's look at an example involving time series data. So the example we're going to use here is just a sequence of noisy sine waves, where moving from left to right, we see that the amplitude of the sine wave is increasing and then decreasing. If you look at the time series on the far left and the far right, you can see that most of the signal is obscured by noise, whereas for the middle portion, you can see this periodic structure more clearly. So we want to see if our method can detect this change where you're seeing mostly noise at the beginning and end, but you're having that signal more clearly in the middle portion. So to get a point cloud to input into our method, we're going to use the time delay embedding. So a time delay embedding is defined for a given time series using a dimension d and a lag tau. So the time delayed embedded point cloud is then the collection of d tuples of points that are spaced tau apart. So to make this a little bit more clear, let's look at an example. So here we have an example. It's just another noisy sine wave. And we're going to pick a dimension of 2. So we want to look at these 2 red points. And our tau is going to be whatever the spacing is between the points here. So we're going to look at the y coordinates of each of these points, and that will give us a tuple of one point on the right-hand side. So we can watch as we shift these 2 points along the time series, we're seeing one new point appear on the right-hand side that has coordinates corresponding to those 2 values. And we can see that this sine wave, despite its noisiness, produces this circular structure on the right-hand side. So the idea of using time delay embeddings with topological approaches is not new. A pretty common pipeline is to start with a collection of time series, embed each one using the time delay embedding, and then compute persistent homology of each point cloud, where here we're just computing standard persistent homology. What this gives you is one persistence diagram per input time series, but the problem becomes, how do you analyze this collection of persistence diagrams? There are existing methods. For example, you can look at maximum persistence, which is the distance from the diagonal to the furthest off diagonal point, and that gives you some sort of measure of how circular a feature is in that particular point cloud. There's also techniques of using machine learning to study persistence diagrams, but none of those quite fit here in this setting because we want to look at how the topological features change through the sequence of point clouds, not just for one particular point cloud at a time. So now we can introduce our method, which we're calling Zigzag Persistence Bifurcation Analysis, or ZPBA for short. So the method starts the same, where you have an input sequence of time series, you embed them using the time delay embeddings, but now rather than computing persistence diagrams for each one separately, you compute the zigzag using this RIPS complex method I've described. And then you use zigzag persistence to extract topological features that persist through this sequence rather than looking at topological features of each point cloud separately. So looking back at the data that we started with, we have these noisy sine waves, and we're going to compute the time delay embedding of each one. And this gives us sort of what we'd expect, knowing that sine waves with periodic behavior produce circular features. We see that the noisy time series on either side sort of just create this cluster of points, whereas the more periodic regions in the middle create circular regions of different sizes. So now we're setting up our zigzag using this RIPS complex method. We're using the same radius for each point cloud. And again, we're looking across rows here, and we can see that starting here at the RIPS complex of x1, we can see that circular feature appearing. And we can see it persist through the rows and persist through each of these point clouds and RIPS complexes until we get to this end. So this is sort of what we'd expect because we knew that there was noisy behavior on either end of this sequence, while the more periodic behavior was in the middle. So the resulting zigzag persistence diagram that we get has a point at the coordinates 1 and 7.5. So again, this corresponds to the fact that the circular feature appears here at x1, persists through the middle, and then disappears going into x8. So we are picking up that region of circularity. While the noisy behavior may cover up the signal on either end, the noise doesn't impact the signal in the middle. Okay, so for our last example, we're going to look at the Selkov model. This is a real dynamical system, so this is the closest to a real-life application. So the Selkov model is a model for glycolysis, which is a process of breaking down sugar for energy. So this model is defined by the 2 equations shown on the slide, where x and y are concentrations of different chemical compounds. So what we're going to do is fix the parameter value a at a certain value, and we're going to vary the parameter value b. And we can see that solving our model, we get very different behavior, where at the end we sort of have steady concentrations of each type of chemical compound, whereas in the middle we get this oscillatory behavior relating between the 2 compounds. So we want to see if we can detect this range. So again, we have our full model here because we know what model we're starting with, but in real life, that's typically not what you have, right? Typically when you're observing a system, you have one recording or one time series. So we're going to fix the parameter value a at 0.1. We're going to vary the parameter value b between 0.35 and 0.9, but we're only going to hold on to the solution, the x coordinates. So we get the corresponding time series shown on the right. For each parameter value, we get one time series. Then we're going to use our delay embedding method, taking those time series and creating two-dimensional point clouds from them. And so we can see that we are reconstructing the dynamics that we saw using the full model, where you get that circular behavior in those middle range of B values from around 0.45 to around 0.75. So now we want to see if our method can extract the behavior that we're seeing. So again, we're setting up our zigzag of these point clouds, except in this case, we're going to subsample because the point clouds shown previously are pretty densely populated. So to improve computation time, we're going to only select 20 points from those point clouds, and we're going to do so using a greedy permutation algorithm. So selecting those points, we get the zigzag sequence shown, and then we apply the RIPS complex to those selected set of points. This is sometimes called the landmark complex. So now we have our zigzag sequence where you can see that circular feature again persisting through this middle range of values. So now we want to look at the resulting zigzag persistence diagram to see if it's picking up the regions that we would expect. So looking at the persistence diagram, we have one off-diagonal point that represents the one circular feature, and it has the coordinates 2 and 8.5. So recalling again that these relate to the index, not the B values specifically, we can map back and see that looking at the second point cloud, all the way down to the 8th and going into the 9th is where that circular feature exists. So this means we're picking up the range of values where the parameter B ranges between 0.45 and 0.8. It is known that this particular model has a bifurcation for the given A value that we fixed ahead of time. It has a bifurcation for the range of about 0.4 to 0.8. So we're picking up most of that region. And if we did a little bit more of a fine-grained analysis of B, we might be able to pick up even closer to that range, because you can see looking at the point cloud for 0.4 and 0.8, you can tell there was probably some circular structure there that was collapsed inward as you progress through the time series. So even at this coarse-grained level, we're able to detect most of the region we wanted. And if we did a little bit more of a fine-grained analysis, we'd probably get even closer. So in summary, our ZPBA method is a one-step process that bypasses this computation of numerous persistence diagrams. What we mean by one step is that you don't have to compute persistence multiple times. You're just computing one persistence diagram that is summarizing the topological information for the entire sequence of point clouds that you started with. So ideally, this would improve computation time because you avoid computation of numerous persistence diagrams, and you avoid the issue of having to analyze those collections of persistence diagrams after the fact. So using zigzag persistence here, we're able to track changing circular structures by looking at the one-dimensional feature in the diagram with the longest lifetime. So we showed 3 examples in this talk where that works. One of these examples is the Selkov model, which is a real dynamical system which closely models real life. Going forward, we would like to apply this to experimental data where you're seeing this behavior occur. We'd also like to improve the computation time so that we are actually improving upon computation of numerous persistence diagrams. And lastly, we'd like to look for some heuristics for choosing the radii value to create the RIPS complexes. For these examples, it was pretty easy to select them by hand, but doing a more large scale application to experimental data, you'd want a more automated fashion to do this. So thank you everyone so much for listening. And thank you to my collaborators, Dr. Munch and Dr. Casone. We're going to have a preprint on this on the archive very soon. It will be under the title Using Zigzag Persistent Homology to Detect Hop Bifurcations in Dynamical Systems. So we don't have a reference for that yet, but if you're watching this talk later down the line, please search for it on the archive if you're interested. Thank you so much.